Describing airplane motion is the basis of flight mechanics. And for that, we need a precise vocabulary to describe, first, the attitude of the body, in which direction the nose and the right wing are pointing to. For that, we will use Euler angles. And second, we want to describe the speed vector in ground coordinates. It is where the airplane is going to. And finally, we also want to describe the speed vector direction in body coordinates. It is from which direction the airflow is impacting the wing. This will be important to determine aerodynamic forces. In this course, we will consider that there is no wind and that the speed relative to the Earth is the same as the speed relative to the ground. So let's consider this aircraft I captured with my phone taking off from Toulouse Airport. We can see that its trajectory is almost linear with a slight upward curvature. At any point, the speed vector is tangent to the trajectory. The speed vector is building the trajectory, and that's why the pilot wants to control the speed vector in order to control this trajectory. But as we can see, the longitudinal axis of the airplane, the dotted black line, is far from being parallel to the speed vector. In other words, the aircraft doesn't go where its nose is pointing to. To define the aircraft attitude, we will use Euler angles. So starting with body and wing level, the nose supposedly pointing to the north, I perform a first rotation about a vertical axis. This angle of rotation is called the heading and noted with the Greek letter psi. Then I will turn around the right wing axis and then around the body axis. Those two angles of rotations are called the pitch attitude, theta, which is positive when the nose is raised up, and the bank angle, phi, which is positive when the right wing is down. I will now define the direction of the speed vector relative to the ground. In the same way, but with only here two rotations, because I need only two rotations to define the direction of a speed vector. Okay? So I start with the speed vector pointing to the north. Then I will perform a first rotation about a vertical axis, and then a second one around an horizontal axis. The first one will define the track of the airplane, and we won't use it too much, as the aircraft is flying exactly the same way when it flies to the north or when it flies to the east. The second one is very important. It is called the flight path angle, gamma. I may say FPA in short. It is far more important, and it indicates whether the airplane is climbing or descending and to which extent. We can also define the direction of the same speed vector, but now this direction is relative to the aircraft body. This will be particularly useful to determine aerodynamic forces. First, we define beta, the side slip, which is the angle between the speed vector and the airplane plane of symmetry. In normal flight, it should be null. And second, we will define alpha, the angle of attack, which is the angle between the speed vector projection on the plane of symmetry and the body axis x. This one is a very important parameter. In the very particular case where bank angle is null, and only in this case, we have this interesting relationship. Theta equals gamma plus alpha. Be very careful, this is no longer true in a turn, for example, as those angles are no longer defined in the same plane. So coming back on the takeoff, we can visualize the flight path angle, which is the angle between the blue speed and the green horizontal line. Then we can define the angle of attack between the speed vector and the dotted black body axis. And finally, the pitch attitude between the green horizontal and the body axis.